Hey guys, welcome back. We just got a few more motors to cover, and then you'll be done with me. You'll be done with all this nonsense here, guys. Okay, and so let's talk about them, get them, under our belt, so that we can move on, write the test, and be, get ready for the CFQ. Okay, guys. So what we're going to do is look at the shaded pole motor. Now, I'm still looking at, the alternator motor notes handout, Unit 5, handout 2, page 16. Shaded pole. All right, guys. Now, what the heck's a shaded pole motor? Well, it's a pretty cool motor, and it's pretty little, usually. Usually you can put it in your hand. It's used in all kinds of household appliances. It is an induction motor, an AC induction motor, single phase every time, okay? Because now we're talking about a couple of different single phase motors again. Now, there's some notes about it here. It's super reliable. It's pretty small. Usually it isn't particularly efficient, maybe 30 or 40% efficient, something like that. Doesn't produce a lot of power, but it's really handy for kitchen fans, bathroom fans, any other kind of light duty motor application where has some really cool features. One is it really runs quietly. Okay, so it's inefficient and small, but runs really quietly. Which is why they use it in fans. And yeah, I mean that's basically it. Okay, it's small and it runs quietly. Now, how does the thing work? Well, I'm going to make a little drawing of it because that's what I do, right, guys? Even though there's sort of some drawings here of it already, let's actually draw it out and see if we can figure it out. Usually when you have a shaded pole motor, it's going to look kind of like this. The first thing it's going to have is the same rotor that every other, induction motor has. It's got the squirrel cage rotor, so big chunk of metal, aluminum bars, okay? But then it's going to usually have laminated steel, magnetic circuit, I guess you could say. That looks kind of like this, okay? And it's going to be connected or not connected. So this is a metal, this is the rotor, right, guys? And there's going to be a winding right here. All right. And that's kind of what you see on, this picture right here, right, guys? Winding, a bunch of laminated steel, and then something to hold the rotor in there, which is just a squirrel cage rotor. Now, if I hook this thing up to AC, guys, what would happen is I would get this alternating magnetic field, right? And we know that alternating magnetic field isn't quite good enough. It doesn't allow the motor to start. And so what they have to do is do another little trick, and that is they take a notch here. They put a notch right about here, guys, on there and on there. It's an actual notch in the aluminum, or in the steel, I should say, okay? And then they put one or two wraps of copper on there, okay? And so there's like and this thing here is called a shading ring, okay? And that's why it's called a shaded pole. Here's the pole face, guys, and there's a shaded ring on there. Now there's going to be another shading ring right here, okay? So those are both shading rings. Now, how does that help? Well, if I take a look at the actual shading ring, well, let's take a look at the AC sine wave for a second, okay? Because we're going to see what happens during the alternation. Now, if I take a look at, one alternation, let's say, okay, there it is. That's being applied to this thing. And right over here, as the voltage is screaming up, okay, the current is screaming up and the magnetic field is expanding crazily here. Let's say this is north right now, and this is causing this to be south, okay? So we're going to look at one pole at a time because that's easier, or just one pole. The other pole is doing the same thing, okay? The magnetic field is expanding out really rapidly, in the first kind of third of the alternation, okay? And as the magnetic field expands, you've got all kinds of flux expanding out, and it's actually crossing the shading ring, and it's actually inducing a voltage into that shading ring. And anytime you have an induced voltage into a ring like that, it's going to have a lot of current flowing in it because it's a short circuit, basically, that loop. Okay, and so you get a bunch of current flowing in there, and that current causes its own magnetic field, and that magnetic field would actually oppose the North Pole that's trying to appear here, okay? And so what you end up with, if I took a, kind of a close-up of that pole face, here's my notch, okay? And all this is trying to become north here. I get, here's my shading ring here. because this shading ring is opposing the North Pole that's trying to appear here, you kind of get a North Pole that sits like here, okay, from here to here. And this sort of isn't doing anything because of the shading ring opposing that, okay? So that's in the first third of the alternation. Now, if you take another third of the alternation, let's say right here, here the voltage is there, okay, but it isn't changing much anymore. It's kind of flat, okay? And so now you have a magnetic field that's appearing across here, and it's not really expanding out or collapsing. It's just sort of there. And because it's not expanding out or collapsing, it's not really inducing a voltage into the shading ring. And so the shading ring is really having no effect. So, the first third, you get sort of this, and then the second 1/3, you kind of get a uniform North Pole kind of appearing across the entire face of that pole there, okay? So you get sort of that. And then you get the third of the alternation where the voltage is screaming down, and so the magnetic field is collapsing again. And once you get a lot of flux movement, and the flux is actually crossing the shading ring again, inducing a voltage in it. But because now the magnetic flux is moving towards the magnetic field instead of away from it, it's actually inducing a voltage such that it enhances the north that was appearing over here. And so for the last 1/3, you kind of get a concentrated North Pole right on the far end, okay? So this is the last third of the 3/3 that make up the alternation, okay? And so you get kind of a north here, and then a north all the way across here, and then a north right there. And it's the same thing here. You get a south here, okay, and then a south just here, and then a sort of a south concentrated right there. And that is enough, rotation to cause this thing to start to want to turn in, one direction or the other. And it'll always turn in the direction of the shading pole, okay? So this drawing right here will cause this rotor to rotate this way. It will always rotate, first here, then there, then there. So you will always get rotation in the direction towards the shading ring, okay? And for that reason, guys, you can't really reverse this machine. The only way to physically reverse it would be to switch the shading rings, right? Move this one down to here. Well, there's no way you're going to do that without taking the whole machine apart. You can kind of reverse it by taking the rotor out and flipping it over, and then the shaft ends up on the other side, okay, of the machine. So you're basically taking the whole thing apart, okay, and you're taking this shaft out and you're flipping it so that the shaft comes out the other way. It's a different motor then, right? But it would be running in the opposite direction then. All right, so you could do that. Okay, guys? Read your notes about the shaded pole motor. Okay, but that's how it works. Now, there is another kind of shaded pole motor that we should talk about, and it'll only take a second because it is exactly the same as this shaded pole motor. The only difference is, guys, that they will build in some magnetic bars, okay? Basically, some steel bars will be kind of impregnated in the rotor itself. And those bars, after it starts spinning, will sort of, match the polarity of the spinning magnetic field. And so once it starts spinning, it'll kind of lock on like a synchronous motor does. And so the Warren clock motor is a shaded pole motor with the addition of these bars that allows it to run at sync speed. Okay, and that's why it's called a Warren clock motor, because they used to be used in clocks. Because if you can get this thing to run at exactly, 1800 RPM, okay, no slipping at all, then you can put some gears on it and run a second hand and a minute hand and an hour hand on it. And it'll run, as long as the frequency doesn't change, it'll run, at a predictable speed. And so you can get a clock to keep accurate time. So, really quick review. Shaded pole motor, guys, very small, lightweight, inefficient, quiet, low torque, okay? Runs at sync speed minus a bit of slip. It runs like any other induction motor. The shaded rings are there to allow it to start, okay? Because without shading rings, it would just be an alternating magnetic field, okay? And you will recognize a shaded pole motor because you will physically see these heavy copper rings on there. Look it up on the internet. Google shaded pole motor. You'll see lots of pictures, okay? Now, the Warren clock motor, identical motor, except for it runs at sync speed, okay? And it does that by adding some metal or ferrous bars impregnated in the actual rotor so that they can lock onto the sync speed of the, stator winding, basically. All right, guys? And we've got one more motor to cover. I wonder if I should just cover it. Let's do it. All right, let's cover the last one, okay? We're going to talk about the universal motor. All right, guys? Now, the universal motor is, well, you'll know you have one, guys, because you'll see that it is an AC motor, but it has commutator and brushes, okay? All our motors that we've learned about so far have all been, induction motors, right? And induction motors, the beauty about them is that they don't have a commutator and brushes. Now, we know that DC motors have commutator and brushes. We learned about that in level, 2, right? Well, basically a universal motor is a series wound DC motor that's running on AC. Now, we're going to do a real quick review of a series wound DC motor, and then we'll talk about why you can possibly run that thing on AC. Now, this thing has all the same characteristics as a series wound DC motor, and maybe I'll have to remind you of that. But let's take a look real quick at a DC motor that's wound series, okay? So here it is. There's the armature, right? And it's got a series winding as the field, right? So this is the armature. This is the field. Now, if you recall from, and you're going to connect this thing to DC, right? If it's a DC motor. And if you recall from level 2, the series motor, it had a few interesting characteristics. The first was that it runs away at no load, right? If you remember from level 2, you turned on your series motor, you have to turn it off right away because the thing will try to run away. And the reason it would try to run away is because it has trouble producing any counter EMF when it's under no load. Because, if this thing's under no load, you're going to have very little armature current because, all motors, the current goes up with load, right? We know that. So this thing under no load is going to have very little armature current. And so because the field is in series with it, it's also going to have very little field current. And if you have very little field current, it's going to be really hard to produce counter EMF. And a DC motor will not have speed limiting unless it can produce counter EMF. Okay, and I'm not going to get into it. Look at your level 2 notes again, but do understand that a series motor under no load will run very, very quickly. Now, how do you reverse a DC motor, guys? I'm going to just tell you. You have two options. You can change the polarity of the armature, which will cause it to run in the opposite direction. Or you can change the direction of the field, which will cause it to run in the opposite direction, the polarity of the field. If you change the armature polarity and the field polarity, the thing will continue to run in the direction that it was running before, okay? And so when I connect this thing to AC, if I look at AC, it has, a positive polarity for a time and a negative polarity for a time. So if I change this thing here to an AC circuit here like this, what I'll get is a positive polarity, which will mean the armature is one polarity and the field is another, is the same, okay? And so let's say that causes it to run, clockwise. For the negative alternation, it will reverse the armature and it will also reverse the field, which will also cause it to run, let's say, clockwise. So the series motor that you learned about in level 2 can be connected to DC and it will run, let's say clockwise. If you connect it to AC, it will also run clockwise. And that is the reason why a universal motor is called a universal motor. It is called a universal motor because it can run on both AC and DC. Now, if you have a hand drill, that is plug-in drill, okay? You look inside there and you notice there's commutator and brushes. Guess what, guys? It's a universal motor, okay? It's running on AC. You will know you have a universal motor because it has a commutator and brushes. All right, guys? Now, what are they used for? Okay? Well, they are used for applications that have, that benefit from the, characteristics that a DC series motor was. And the characteristic of a DC motor is, it runs away at no load. In other words, it runs like a bat out of hell if you need it to, okay? It's going to scream, this thing, under no load, which is why, your vacuum cleaner in your house is screaming away, and your blender. Those are both, appliances in your house that have universal motor in it, and they are taking advantage of the fact that it is running at 30,000 RPM under no load, okay? And that is a desirable effect, and they just build it so that it can run there and not, blow apart, okay? Your blender, your vacuum cleaner, a router if you're a woodworker, okay? Those are, your skill saw, your circular saw, all these plug-in tools are all universal motors. The other characteristics that a series motor has was it can produce a ridiculous amount of torque. And the reason it produces so much torque is because the armature and the field are connected in series. And so if you start to load this thing up, the armature current goes up like crazy, right? But the field's in series with it, and so there's only one current. So if you have tons of armature current, you're going to have tons of field current, and you need two magnetic fields interacting to produce torque, right? You can't just have armature increasing in magnetic field and the field being fixed. The fact that these two get stronger together the more load you put on it causes it to produce unbelievable amount of torque. And that's why, if you have a plug-in drill, guys, and your bit gets stuck, it breaks your wrist or it breaks the bit off, right, guys? It has tons of torque under load. And that's a real nice characteristic for drills, for, a lot of wood tools and stuff like that, where you're not that concerned about speed regulation. And speed regulation, guys, is like, how good is it at maintaining a certain speed? An induction motor is really good, right? An induction motor under its full load range is going to go 1750 to 1775 RPM, something like that, okay? This thing here, under no load, it's going to run 30,000 RPM, and under full load, it's going to run 300 RPM, okay? So there's this ridiculously terrible speed regulation of this motor, okay? But as it slows down, it just produces more and more and more torque, which is a nice feature for a drill, where you don't really care if it's turning fast or slow. You're just happy that it's turning, right? And this thing will turn. A universal motor produces tons and tons of torque, okay? So I'm not going to kill you anymore with the universal motor. This video is long enough now, okay? But Unit 5, Handout 2, page 18, there's the universal motor. Read all about it, okay, guys? And then your homework assignment for the Warren clock, for the, I'm having a brain fart here. Shaded pole, Warren clock, and universal motor, Unit 5, Handout 6, okay? And guess what, guys? There's a couple of more. I'm going to have to make one more video, okay, so that you can do this motor calculations 1. We'll talk about that one in a second. And your test is coming up, right? Unit 5, Handout 8 is the review, and it's going to be multiple choice. Okay, come back for the last video. It'll probably be really short.